Well, hi everyone. In this video, I would like to give a couple of examples that are actually exercises from the textbook about linear dependence and linear independence. The examples I'd like to do involve a very theoretical perspective on these concepts, and I find that very often students need a little extra practice to understand how to write up a proof involving these concepts. Just to remind you, linear dependence, which I abbreviate as LD, and linear independence, abbreviated with LI, have fairly sophisticated definitions. And I've reminded you here of sort of one perspective on linear dependence of a set of vectors in a vector space. So let's review this definition, and that'll put us in a better position to take a look at the two examples that I'd like to do in this video. A set of vectors v1, v2, all the way up through vn is considered linearly dependent, in other words, LD, if there exist constants c1, c2, and so on up through cn that are not all zero, such that c1 times v1 plus c2 times v2 plus etc. plus cn times vn is equal to 0. So in other words, to put that in simple terms, this is just really saying that a set of vectors will be linearly dependent if you can make a linear combination of them that cancels out without simply putting zeros as scalars in front of all of the vectors. So that's what this not all zero is about, and that's very important in this definition of linear dependence, that we have what I'll call a non-trivial linear combination of the vectors that is canceling out. So when that happens, the vectors are linearly dependent. It's kind of a bad thing, roughly speaking, but what I want to do now is try to turn this definition on its head and write down a definition of linear independence, which is really just taking this definition and flipping the definition around, but still looking at it from kind of this same point of view. So let's write down what linear independence would mean. Linear independence would be a set, again, v1, comma, v2, comma, dot, 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 up to vn. And this set of vectors, right, is Li, or in other words, linearly independent, if whenever c1 times v1 plus c2 times v2 plus dot, 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 plus cn times vn, whenever that does happen to cancel out to 0, then there's only one way that could have happened, which is that all of the constants actually were equal to 0. In other words, the only way that you can cancel your set of vectors out in a linear combination is in the trivial way where we simply put zeros as all of the coefficients of all of the terms in that linear combination. So, of course, when we take this linear combination, c1 times v1 plus c2 times v2 and so on, and we set it equal to 0, we can all see that that would be true if all of these constants were 0. But what this definition is saying is that my vectors will be Li if that's the only way that you can get your vectors to cancel out in this linear combination. Okay, so this turns out to be a very useful way of thinking about linear independence when we're trying to prove things with it. So having rephrased this definition now, what I'd like to do is practice it on a couple of examples over here. Let's imagine that we have a set of vectors v1 through vn that is linearly independent to begin with. These are vectors, let's say, in Rn. And then let's imagine that we have an invertible n by n matrix A. Okay? then what I can do is I can take the matrix A and multiply it by all of those vectors, and I can see right now that I have miscopied what those vectors are. These vectors should be AV1, AV2, and so on up through AVN. So in other words, if I take my original vectors and I pre-multiply each of them one by the matrix A, then we make a new set of vectors, and the statement is that as long as A is invertible and as long as the original vectors were Li to begin with, then this new set of vectors will still be Li. So this is a theoretical problem. It's one that we need to do pretty much from an abstract definition, like the one that I've kind of recapped here in this box just a moment ago. So what I'm going to do this problem is I'm going to take this set of vectors that I would like to prove are Li, and I would like to imagine that they do in fact cancel out in a linear combination. So for my solution, I am going to assume that C1 times AV1 plus C2 times AV2 plus plus Cn times AVN is equal to 0. I'm going to imagine that these vectors do cancel out in a linear combination. And to convince myself that those vectors are Li, I need to show that all of the constants are 0. In other words, that's required. It's forced. It's the only way this could have been true, right? So let's take a look at this. In order to prove that all of the constants are 0, I'm going to start with just a very brief algebra step. You notice that every single term on the left side has the matrix A in it. Well, you can certainly factor that out into the front of the matrix by slipping it past the constants that you see in front. So I'm going to write this as A times C1 V1 plus A times C2 V2 and so on plus A times Cn Vn equals 0. And then I'm going to go ahead and factor the A all the way out of the far left of everything. So we'll have A times the quantity C1 times V1 plus C2 times V2 and so on plus up to Cn times Vn is equal to 0. Remember, my goal is to show that all of the constants are 0. Okay? Now, A is invertible. Okay? So if you want to pause the video and think about how we could maybe use that here, that is the next step, is to use the fact that A is invertible on this equation that we've just written down. So feel free to go a little slower if you'd like to. Think about it for yourself for a moment. But the idea is, of course, that when you have an invertible matrix, you have an A inverse that you can work with. And if I left multiply this equation on both sides of the equal sign by the inverse of A, I can essentially cancel it from this equation. Okay, so that's exactly what I'm going to do. I'm going to take A inverse times A times C1 V1 plus C2 V2 plus plus Cn Vn. And of course that equals A inverse times 0. So I've put an A inverse on the left of both sides of my equal sign. A inverse times A is just the identity matrix, which we remember is like multiplying by 1. So I can essentially drop that. And if I take A inverse times the 0 vector, I will still have the 0 vector. Okay? So what am I left with at this point? What I'm left with, I'm going to go ahead and erase the A inverse times A here, and I'm going to erase the A inverse times 0 here. I am left with the equation that you see displayed here now, which is that C1 times V1 plus C2 times V2 and so on is equal to the 0 vector. But what else are we assuming here in the black writing at the top of this problem that we haven't really incorporated yet? Again, feel free to pause for a moment and think about it if you need to, but we have not used the assumption yet that the original vectors, V1 through Vn are Li. They are given as Li. And so what does that mean? If they are given as being Li, it says whenever they cancel out in a linear combination, then look what we get to conclude. We get to conclude that all of the constants are 0. And so that's going to be the last step. Since V1, comma, V2, comma, dot, 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 up to Vn is Li, we conclude that all of our constants are 0. And that's usually on these theoretical linear algebra, these theoretical linear independence proofs, that's usually the punchline that signals that you are at the end of your proof. If you've managed to show that all of your constants are 0, you're in good shape. Remember, we started with a linear combination of these vectors right here on the second line with coefficients of C1 and C2 and C3 and so on, and we ultimately proved that those constants are all 0. That is, in a nutshell, how a proof of linear independence works when we're doing something in a theoretical way. Okay, so that's a nice example. I want to do one more, and I've got it here on the bottom of my board, and it's kind of set up similarly. We're assuming that something is linearly independent, and we're going to try to prove that something else is still linearly independent. So in that sense, it's very much similar to the problem that we just worked on. Again, I'm going to set this up the same way, guys. I'm going to start by making a linear combination of these vectors V1, V2, and V3, which I'm hoping to prove are Li. So for this, I'm going to, just like on the last one, I'm going to assume that C1 times V1 plus C2 times V2 plus C3 times V3 is equal to 0. And again, the punchline that I'm looking for is to try to prove that all of the constants are 0. In other words, that that's the only way that you could have canceled these vectors out in this linear combination, right? There's no interesting way to do it, and therefore the vectors are going to be Li. Okay, I'm going to explain this using a couple of possible cases here. It turns out, let's just look for a moment at C3. If C3 was not 0, now remember, we are hoping to show that C3 is 0. Let's play devil's advocate for a moment and imagine that somehow it's not 0. Okay? Well, if it's not 0, then would you agree that we can write in that case the V3 vector, we could actually solve for it in my previous line. Namely, it would be negative C1 over C3 times V1 minus C2 over C3 times V2. This is literally nothing more than algebra, taking the first equation and solving it for V3 by moving everything to the other side of the equation and then dividing by C3. Of course, as long as C3 is not 0, dividing by C3 is just fine. Now, I should read this question very carefully because the question assumes that V1 and V2 alone are Li, and that V3 is not in the span of the first two vectors. In other words, if you add another vector to a set, so if you have a set that's already Li and you want to add another vector to it, that new set will stay Li as long as the vector that you added is not already in the span of the first two vectors. But you know what this equation is basically telling us? It's basically telling us that we can write V3 as a linear combination of V1 and V2. It's literally what this expression is. And if that's the case, then that means that V3 is in the span of V1 and V2. Remember, the span of V1 and V2, that's just all of the linear combinations of V1 and V2, which is what we seem to have right here on the right-hand side. So if C3 was not 0, then we would be able to write V3 as some linear combination of v1 and v2. But we're assuming in the original question here that we cannot do that. And so this would end up being what we would call a contradiction. So we have made a contradiction here, and from this contradiction, we would now conclude that C3 must equal 0. We can conclude that, right? So if C3 was not 0, we end up going down some rabbit hole that leads to a contradiction of our assumptions. So we conclude now that C3 is 0. Now, if C3 is 0, we can come back to the starting equation here and literally put in 0 for C3. And if we do that, then what we would have is just C1 times V1 plus C2 times V2 is equal to 0. So there is no C3 V3 term once I've concluded that C3 is actually just 0. Well, what do I have right here? What I have right here, guys, is a linear combination of just the first two vectors, v1 and v2, that's canceling out. It's canceling out, right? But what does this say over here about linear independence? Well, if I have a set of vectors that is linearly independent, then all of the constants involved in this linear combination must be 0, right? Remember, we're assuming here that v1 and v2, just those two vectors alone, are already Li. And so if we have a combination of just those two vectors that is canceling out, then we can conclude that the constants are 0. So since the set v1 and v2 is Li, right, we conclude that C1 and C2 are both 0. And of course, we already knew that C3 was 0, and so all of the constants are 0 again. So in both of these proofs, we've kind of finished our proof with the conclusion that all of the constants in this linear combination that we started off with have got to be 0, right? So I know that when we're working with specific vectors in a vector space, we have ways of deciding if vectors are LD or Li by just putting those vectors into a matrix and doing calculations. But sometimes it's helpful to have a more theoretical understanding of those definitions so that we can do problems like this where we don't really have specific vectors in mind, but rather it's a much more broadly applicable theoretical result. So that's why I'm kind of a champion for the theory. I think it's important, and I really urge you guys to keep wrestling with these definitions of linear independence and linear dependence because it's easy to just kind of shove these aside and focus on the computational aspects of these problems without really understanding what's going on. And I really would like you to understand what's going on. So that was the purpose of this video. I hope that these two examples illustrating the use of these theoretical definitions make sense. But if not, feel free to shoot me a question. I'll be glad to try to help you out further. In the meantime, thank you so much for taking the time to watch this video, and I'll see you all again very soon.